Question 3 from the 2025 Advanced Higher Physics Examination from the SQA. A pulsar is a rotating neutron star that emits radio waves with its magnetic poles. An artist's impression of this is shown in the diagram figure 3a. Now, PSR B1919 plus 21 is a spherical pulsar of approximately uniform density with the following properties. It's got a period of rotation of 1.34 seconds, it's got a mass of 2.8 times 10 to the power 30 kilograms, and it's got a radius of 9.74 times 10 to the power 3 meters. And we've got to show for 2 marks that the angular velocity of PSR B1919 plus 21 is going to be 4.69 radians per second. Well, we start off with an expression for the angular velocity. The angular velocity omega is always equal to 2 times pi times the frequency. And we also know that the frequency can be written as 1 upon the period t. So we substitute the frequency for 1 upon t. We end up with the angular velocity omega is going to be 2 pi divided by t. So we've got all the information there. We can put in now the numbers. Omega is going to be bracket 2 times the value of pi, which we'll put in 3.14, and we'll divide that by the period t, which is going to be 1.34 seconds. 1.34. So when we do that in our calculator, we end up with an answer of 4.689, and that'll be radians per second. And to put it to 2 significant figures, we can put that as 4.69 radians per second, and that's what I've been asked to prove. 4.69 radians per second. Question 3, part B. Calculate the moment of inertia of the pulsar. Well, we have the moment of inertia for a solid sphere because we're taking it to be a solid sphere. The question information tells us that it's got a uniform mass. So therefore we know that the moment of inertia for a sphere I is going to equal to 2/3 times the mass times the radius squared. So we've got all the information, we've got the mass, we've got the radius, so we can work out what the moment of inertia is. Moment of inertia I equals 2/3, and we multiply that by the mass of the pulsar, which is up here, 2.8 times 10 to the power 30, so 2.8 times 10 to the power 30. And we have to multiply that by the radius squared, which is 9.74 times 10 to the power 3, so 9.74 times 10 to the power 3, and we have to all square that, so square that radius like that. It's a calculator problem, so we plug that answer into a calculator, and we end up with the moment of inertia of the pulsar is 1.77 times 10 to the power 38, and the units will be kilograms and meters squared. Question 3, continued part C. The pulsar was formed when the core of its rotating parent star collapsed under its own gravity. When this occurred, the loss of mass from the core of the parent star was negligible. And for 1 mark, we have to state the principle of conservation of angular momentum, which is very similar to the statement for the conservation of linear momentum. And here is for the angular momentum one. We have provided no external torque acting on the system. The total angular momentum before is equal to the total angular momentum afterwards. In expression form, I1 omega 1 equals I2 omega 2. And that's for 1 mark. For question 3C part 2, it says the core of the parent star had a moment of inertia of 2.7 times 10 to the power 42 kilogram meter squared. And we have to determine the angular velocity of the core of the parent star immediately before it collapsed. Well, to do that, we have to do a little diagram, which you can do on here. So we'll draw the diagram here, and we'll bring in the parent star, which is going to be rotating round, and also the collapsed star into the pulsar here. Now, what was the information before? Well, we can put in omega 1, that's going to be the angular velocity before the collapse, but we do know that the moment of inertia of the star before the collapse was given by that expression there. I1 is equal to 2.7 times 10 to the power 42 kilogram meter squared. And after it collapsed, we know that the angular velocity of the pulsar was 4.69 radians per second. We were told that in our example. And then we also know that the moment of inertia, which we worked out for the collapsed star, was 1.77 times 10 to the power 38 kilogram meter squared. So it's straightforward to use the equation. So we can put in the expression. We know that I1 times omega 1 must equal I2 times omega 2. Now we're after omega 1, so we can just rearrange and get that omega 1 has got to equal to I2 omega 2 and divided by I1, the moment of inertia before the collapse. Just put the numbers in and we get the following. We get I2 is going to be 1.77, we'll put this in brackets, 1.77 times 10 to the power 38. And we're going to multiply that by omega 2, which is going to be, in this case, 4.69. That was the angular velocity after the collapse, 4.69. We have to divide that all by the initial angular momentum, which is moment of inertia, I1, and that's going to be 2.7. So it's going to be 2.7 times 10 to the power 42. Now we do that in my calculator, we end up with the omega 1, the initial angular velocity, to be 3.07 on my calculators times 10, and it's going to be minus 4, and it's going to be radians per second for the units. Radians per second for the units. Question 3, continued part D. Using your knowledge of physics, comment on the similarities and differences in the evolution of stars into neutron stars, black holes and white dwarfs. What's the similarities? The similarities are the following. All these objects started off as dust, nebulae as we call them, and this dust collapsed under their own gravity to become protostars, young stars. And these stars all began their life on the main sequence, and they used up their nuclear fuel. And as they used up the nuclear fuel, they collapsed under their own gravity because, of course, the outward pressure was not there. So these are the sort of things you could mention for the similarities. What's the differences? Well, the differences is basically how these objects came about depended upon the mass of the star which was collapsing. And the white dwarf mass, well, to become a white dwarf, the star must have roughly 1 to 8 solar masses. Of course, our sun is 1 solar mass, so we'll end up as a white dwarf. And also a neutron star, if the star had between 8 and 20 solar masses, it's going to end up a neutron star. And finally, if it's got even bigger mass than that, 20 solar masses and beyond, when that star collapses, it's going to become a black hole. Now, it's only for 3 marks. You don't have to go into a lot of detail, but that there should be enough to cover you for the 3 marks.